Hey guys, welcome back to Crick Code. Today we're doing another Brainstellar Quant puzzle. This one is called Collecting Lucky Coupons. It's another hard problem. Let you guys pause and go over the problem. So basically in the problem, we keep getting numbers from a set of 1, 2, all the way up to n. So let's say the first n natural numbers, right? Now from this set, we keep getting an in stream of numbers. So let's say we first get a 1, then a 4, then 5, 2, 3, 1, 4, 1, 1, 3, and so on, right? We keep getting numbers from this initial set. And this set is an infinite set, which means that there's an infinite amount of each of these numbers from 1, 2, 3, all the way up to the number n, right? And for each new number that we get, so first of all, we get 1, and then we get 2, and now we're waiting for another new number, right? Now, for each new number we get, the probability of this number being any number, so let's say just x, and x maps from 1 all the way to n, right? X belongs to this natural number set, and the probability of getting x as the new number is always going to be 1 over n. Well, you can think of it in this sense that for each new number, there's an equally likely probability of getting any one of these numbers from this infinite set, right? That's why the probability of getting any new number is 1 over n. And what we've been asked is the expected number of numbers that need to be inputted or inserted or drawn from this infinite set over here in order to achieve at least one number of each value from 1 to n. Now, what I just said means that, so we have this infinite set and we keep on drawing one number from it, right? We first draw 1, then a 4, then a 5, then a 3, and so on, right? And now, so these are the number of numbers we've drawn already. Now, what we've been asked is, well, first of all, you keep on drawing numbers until you get at least one number of each type. So let's say n was equal to 5, right? Until we get a 1, a 2, a 3, a 4, and a 5. Until we get all of these 5 distinct values, we keep on drawing numbers. And once we get all those 5 values, we stop there and look at the number of numbers that we needed to draw in total. And what we have to calculate is the expected number of that value. So the expected number of So this is actually what we're asking. The expected number of draws required to get at least one instance of every number from 1 to n, where draws is just taking out a number from this infinite set from 1 to n. So for a random example, taking n is equal to 5, the numbers we draw are 1, then 5, then 4, then 3, then 5, then 2. Then this took us a total of 6 draws in order to get at least one instance of every number, right? Now coming towards the hints. Well, first of all, there's one big hint. They're using a general value n, so it's always beneficial to look at simple cases of 1, 2, 3, and so on. And we might just be able to come up with a recursive solution. So for a recursive solution, we always need to define a state, right? Or an e of something, which basically becomes the representative of a state. So this value inside can be a state, and what we're asking is the expected value of this over here, this value for the given state that we're at. So imagine this situation. So out of n numbers that are possible, we just need x more distinct coupons or numbers. Well, the problem originally was talking about coupons, but I just changed it to talk about numbers. But yeah, so imagine that we're currently at a state where out of the n initially required numbers, we just need x more distinct numbers. So that for concrete example, that could be for n is equal to 5, we already have 3 and 4, and we just have a value of x is equal to 3, which basically means we need 1, 2, and 5, right? So I'm trying to define the state as, given the numbers we already have, x is the number of distinct numbers we still require. Thus, we define the state as e of x, right, as the expected number of coupons or numbers or draws that we will have to do from this point onwards to obtain those x distinct values. So let me just write that down. So this is how we're defining a state, and we're going to use this in our recursive solution. Now notice here that the value of x can be anything, and it doesn't really matter on what actually is x referring to. So for the example we had earlier, I said that we already have 3 and 4 and we need 1, 2, and 5, right? But x is equals to 3, right? Now when we say x is equal to 3, this does not encapsulate the information of we requiring 1, 2, and 5. This could be any 3 values. But since all of these numbers are symmetrical, it doesn't really matter what exact values do we require. All that matters is the total number of distinct values, which is denoted by x, that we still require. What I'm trying to say is, given we already have a 4 and a 5, and we require 1, 2, and 3, or given we already have 1 and 2, and we are yet to obtain 3, 4, and 5, these two states are completely identical for us because the numbers in itself are completely symmetrical. So this is going to be represented by x is equal to 3, and so is this case. What I'm trying to say is these two cases are completely identical because all that matters is the number of distinct values that are yet to be obtained. So let's start off with the value of e of 0, right? Well, it's pretty simple, right? Because this just means the expected number of draws that we will need to do in order to obtain 0 new distinct values. Well, this is obviously going to be 0, right? We have our base case. And notice that the actual value, the answer to the problem, initial problem, is e of n. The expected number of draws we will be required to do in order to obtain n new distinct values, right? This was the initial question that we had. We have to find the answer to this problem. So if we look at the general state of e of x, and now let's try to talk about the recursive logic. So this state over here means that we're still waiting for these x new distinct values, right? But this also means that out of the set of n values, right, there are n minus x values that we have already obtained. This implicitly implies this, right? If we are waiting for x new values, then we have already obtained n minus x distinct values. Now notice among these n minus x values that we've already obtained, there could be multiple instances of any value, but it doesn't matter. Overall, we have n minus x distinct values already with us, and we are waiting for x new distinct values. Now, since at this step, the probability of each number, right, at any step rather, no matter how many numbers we already have, for the new value, the probability of any number is 1 by n. And we want, and our favorable outcome is to get any of those x values, right? And our non-favorable outcome would be to get any of those n minus x values. So if I were to say that we're currently at e of x, now, if I on the next turn get a value which belongs to these x distinct values I'm still waiting for, well, then this e of x is going to reduce. As in, so let me just write this down. There's a chance that we get a new value. So that would be denoted by the probability of new value. Now, what happens once we get a new value? We already had n minus x values. We were waiting for x more. And now we got one of these x values. So that just means that we took one draw, right? Because obviously taking out this number would be counted as one draw. But now we're left with e of x minus 1 because we got a new value over here. And for the new state that we're going to reach, we're only going to require x minus 1 new values. And now the other case is going to be the complement of this thing, right? The probability of getting an old value. Now what's going to happen in this case? Well, we used a one draw to try and see if we get a new value. We didn't get a new value, and the effective state that we reach at is going to be e of x itself. Why is that? Because at the state of e of x, if we get a new value, then we basically reach the state of e of x minus 1, right, which is denoted here. And taking up a new draw is also denoted by this plus 1. But if we get one of those n minus x old values, that means we didn't get a new value which was among those x new values. Well, that just leads us to e of x again. At this state, since we didn't get any new values, we still are waiting for x distinct values. And this is denoted over here. And this plus 1 is because we had to draw one number in order to reach the new state, but that new state was again e of x. So simplifying this over here again, e of x is going to be something, let's just call it y. Y is going to be denoted as the probability of getting a new value into 1 plus e of x minus 1, denoting that, okay, so y means we got a new value. So that means that we go to the state of e of x minus 1 plus 1 minus y, the probability of getting the same old values into 1 plus e of x. E of x, because we come back to the original state, we still are waiting for x distinct values. Now, the only thing that we don't know is y. So y is this over here. So y is basically the probability of drawing one of the x values we were wanting, right? Now, you tell me, so if we have n total values, and among them there's x values that we are wanting, then what's the probability of getting one of those favorable outcomes? It's going to be x over n, obviously, right? Because each of these values has a equal probability of 1 over n. And if we are happy with any of those x values among all of these n values, then the probability of getting one of those values is going to be x over n. So our equation simplifies to this over here. And if we solve this, we get e of x is equals to n over x plus e of x minus. Now, if we expand this for values of going from 0 all the way to n, e of n becomes n over n minus n minus all the way up to n over 1 plus 0. And we can stop at this over here, but there's this formula that we could apply to approximate the value. So if we take out n, this turns out to be 1 over n plus up to 1, right? And this can be simplified to approximately log of n. So this value of e of n approximately n log n. But there's really no need if you can stop over here if you get. So this is the approximate value. I hope you guys understood the solution, and thanks for watching.